we're going to be doing some Unit 4 AP Physics 1 practice problems. So let's say we have, a 3 kilogram object is moving along a straight horizontal track at a constant speed of 4 meters per second for 5 seconds. The linear momentum of the object is most nearly, so we know that the formula for linear momentum speed is vector of p times times the vector v. The magnitude of this is just pmv. So p is equal to the mass is 3, 4, we have 12 kilograms times meters per second. So that's going to give us 12. A. The force graph represents the net force exerted on a box as it slides across a tabletop. Which of the following expressions correctly represents the impulse delivered on the box during the time interval shown in the graph? So we know that impulse is defined as the area under the curve of dt area under curve, but it's AP Physics 1, so you don't have to do that. You don't have to do the integration. So we see that the area is a trapezoid, so we know the area is going to equal to 1/2 of f1 plus f2 is tf. So then we can just plug in our values. So that's just going to be f1 plus f2 minus 1 over 2. So we have, so we can write J is equal to f1 plus f2 minus f1 over 2 is tf. Now we can, f1 plus 2, f1, this part specifically is equal to that. So this, we can see that this is clearly option D. Sorry, kind of lagging there. So a block of mass MB is moving right with speed v initial on a smooth horizontal surface as shown. The block is struck by a lump of clay of mass MC, moving horizontally with speed 2v initial, which sticks to the block. Which of the following is the correct expression for the velocity of the clay block system immediately after the clay sticks to the block? So we know that there is going to be, so horizontally, it sticks, so we know it sticks. If it sticks, then we know that it is a perfectly inelastic collision. And what is a characteristic of a perfectly elastic collision is that we have the conservation of momentum. So momentum is conserved. So that means that P initial is going to be equal to P final. So then our initial momentum, P initial, is going to equal to MB V initial plus MC. So the ball, mass of the ball times the initial velocity times mass of the clay times 2 times V initial. So you can see here MC is 2V initial on B, M initial, so that's going to be the initials. So the PF, and then we know that because they stick together, we can write the masses together. So then we have MB plus 2MC V initial, and we know that they're moving as one block now, so they can one block can only have one velocity. So then we know that the combined mass is going to be MB plus MC. So then we know that again, PI initial. Oh, this is for PI initial. That's combined mass. That means we can write the PF is equal to B plus MC VF. It's basically the same thing. So solving for the final velocity, we can divide both sides by MB over MC. So we have that V initial is going to, for PF we have, for PF we have that. So we have MB plus 2MC v initial, that's going to be equal to mb plus mc vf. That's going to be from vf. Okay, what am I doing? mb plus 2mc over mb plus mc v initial. So rewriting the numerator, we can just make it match. We can see the answer over there. 2mc plus b over mc plus mb v initial. Whoa, okay. So, two blocks with masses and speeds indicated in the figure move toward each other. There is a negligible friction between blocks and horizontal surface. The blocks collide and stick together. How much mechanical energy is lost during the collision? So, block 1, we can see the mass is going to be m, and the velocity is 2v. And block 2, we can see the mass is going to be 2m, and the velocity was just negative v, right? If we, because we just this is positive y, this is positive x. Now they move forward together. It's again, it is frictionless, and they collide and stick. So this is a perfectly inelastic collision. So then if it's perfectly inelastic, then we can use momentum conservation, right? So then we can write out the initial momentum, which is m times 2v plus 2m negative v. Here, see 2v and 2m negative v. Now we can write this again as 2mv minus 2mv is equal to 0. And then we can write our final momentum. So post stick, we have that m plus 2m vf is going to equal to 3m vf. Right? So then we have, if we set them equal to each other, we have 3m, okay, we set p initial equal to pf, right? Then we get that 3m vf is equal to 0, so then vf is equal to 0. So now we can compute the kinetic energy, right? So we have k is equal to 1/2 mv squared, so you have k1 is equal to, okay, so this is for block 1. And then for block 2, so k1 is equal to 1/2 2v squared. That's going to equal to 1/2 4v squared. That's going to equal to 2mv squared. And here for block 2, you're going to have k2 is equal to 1/2 2m v squared. It's going to equal to mv squared. And now the kinetic initial energy total is going to be equal to 2m v squared plus m v squared. It's going to equal to 3m v squared. And we know that the final kinetic energy is equal to 0, right? And then we can show the total energy to find the mechanical energy loss. That's going to be k initial minus kf, and k initial, we know that was just equal to 3mv squared, and the kf is that, so we have 3mv squared. And where's that? 3mv squared, that's going to be option D. An elevator at rest at time t equals 0 begins moving upward at a constant positive acceleration. Which of the following graphs could represent the linear momentum p of the elevator as a function of time? So we know the elevator, it starts at rest at t equals 0, and then it moves, okay, constant positive acceleration. And we're asked what graph could be linear momentum p versus time. So we know that the definition of momentum is p is equal to mv, right? And then we know that under cake, when we're looking at velocity is equal to at. And we know this is since v initial is equal to 0 from the cake equation. And we can substitute that in. P is equal to m times a of t. And we have a of t. So therefore, we know that the momentum starts at 0. The momentum increases linearly with time, and there is a straight line through the origin, constant positive slope. You can see that's clearly just option B. 6. A cart with mass 0.25 kilograms moves along a straight horizontal line aligned with the x-axis as shown in the top figure. The cart is initially moving in the negative x direction with a speed of 10 meters per second. A horizontal force is exerted on the cart in the positive x direction for 0.02 seconds. The graph shows the magnitude f of the forces as a function of time. Which of the following correctly indicates how the magnitude of the cart's momentum and the direction of the cart's momentum have changed, if at all, at the end of the 0.02 second interval? So we have mass and the initial velocity. We're going to say that's negative 10 meters per second. That's positive x, that's positive y, so that's negative 10 meters per second. So the force is applied in the positive x direction. And okay, the force time is going to be a triangle. Your time interval is going to be from 0 to 0.02 seconds. So we're asked, did the momentum change and also the direction? If so then what we can do is we can write the initial momentum, which is equal to pi, which is mv, and the mass is 0.25, and that's velocity is negative 10. So then you have negative 2.5 kilograms meters per second. It's measured in meters per second. And now we have to calculate the impulse from the force time graph. The impulse is equal to the integral of f dt. Again, the area under force time graph, right? And the graph is a triangle. So we can just 1/2 base height this. So your base is going to be 0.002 seconds. Your height is going to be 2,000 newtons, right? So then that's going to be equal to divided by 2, 1,000 times 0.02. That's going to be 2 newtons second, and then positive. So that's the impulse direction. And then the final momentum that you have, Pf is equal to P initial plus the impulse that you exerted. So that means Pf is going to equal to negative 2.5. It's supposed to be J plus 2. So that's going to be equal to negative 0.5 kilograms times meters per second. So then we can interpret the results. So we know that the P initial magnitude, that was negative 2.5 kilogram. We want just the magnitude, so it's 2.5, and then the PF magnitude, that's negative 0.5 kilograms. We just want the magnitude. That's it. So that means we can see that the magnitude altitude, it decreases. So therefore the direction, okay, so the direction is still negative, still left, and didn't change. So where can we see this? So we want still negative, still left, and did not change. Okay, we're looking for, so you see did not change. It's still negative. Okay, it's decreasing. So we can see that that's answer option B. So, like, we can move on to our next problem. A person with a mass 80 kilograms stands on a raft with a mass 15 kilograms that is initially rests on a still pond. The person begins to walk forward on the raft with a speed of 5 meters per second as shown. What will the resulting velocity of the raft as the person be? What will the resulting velocity be as the person walks forward? So, the person's mass, okay, 80 kilograms. I'm just put it up here. MP is equal to 80 kilograms. The raft is going to be 15 kilograms. Okay, it's initially the system. It's initially at rest, and then this person is moving positive 0.5 meters per second relative to the ground. And also, the pond is still. Okay. So there's no external horizontal net force. So that means that if there's no horizontal forces acting, then you have P initial is equal to PF, right? And it starts at rest. And the final momentum, PF, is going to equal to MPVP plus MRVR. And VR is unknown, so if we substitute in our values, we know that PI, PF have to be equal to each other, therefore PF is going to equal to 0 too, right? So then you have 80 for your person's mass, you have the velocity was, and then you have 15 for the raft, VR, that's going to be 0 plus 40 plus 15 VR, then you have 15 VR, so negative 40. Then we have the VR is going to be equal to negative 2.67 meters per second. So what does this negative sign mean? It means that it is opposite the direction of the person's motion. That is going to be 2.67 meters per second. That is A. The graph shows the velocity v of a car as a function of time t, where the positive direction is to the right. Which of the following correctly indicates the direction of the momentum of the car during the two time intervals shown? So what we can see is what we know is the velocity is always positive. And that's because it's always up here. If it was negative, it would be down there. So, and the positive direction is to the right. So we have two intervals. We have this interval right here, and we have this interval right here. And we know that the relationship for momentum, right, is the vector P is equal to the mass vector V. And that means that we know that the direction of the momentum is equal to the direction of the velocity. Same direction. So we can see here from 0 to t1, we can see that the velocity is positive v, and the momentum is to the right. And then here we can see that the velocity is still positive and the momentum is still to the right. So we can see that matches with D right here. So we can choose D. A puck slides from to the left with speed v initial on a flat surface toward a foam barrier shown, and there is a negligible friction between the puck and the surface. When the puck reaches the barrier delivers an impulse J initial to the puck, and the puck comes to rest. The foam barrier is replaced with a hard barrier, and the puck again slides toward the barrier with v initial. When the puck reaches a barrier, it bounces off the barrier and slides to the right with speed v initial. Which of the following indicates the impulse delivered to the puck by the hard barrier? So, the puck is mass m, and we know that initially it's sliding left with v initial, and then after that, that's not, it's sliding left with v initial, and then we also know there is negligible friction. The foam barrier case, it stops, and then the impulse delivered, that's equal to J initial. So the hard barrier case, it bounces. So, and then it bounces back. So then the final speed, VF, is equal to V initial to the right. So we want the impulse delivered by the hard barrier. So the definition of impulse is J is equal to delta P momentum equals to PF minus P initial. So we know that the initial momentum, P initial, was equal to negative mass times the velocity. Well, it's negative because that negative actually belongs to the velocity, positive y, positive x. It's going right, so that's negative direction. So, and the final momentum is going to be equal to 0. So the impulse, J initial, is equal to 0 minus negative mass, V initial. And then, yeah, because we just want to change that formula up here. Yeah. So then we can write this as V initial. So then we know that's equal to J initial. So now this was for the foam barrier. Now, okay, for the hard barrier, we have the initial momentum is equal to the negative m v initial, and then PF is equal to positive m v initial, right? So then the impulse, that's J, is m v initial minus negative m v initial. That's going to be 2m v initial. So then we can substitute in, we know that mv initial is equal to J initial from up here. So everywhere we see the mv initial, we can sub that in. So we have J is equal to 2 times the J initial, right? And we can see that matches with answer option D. So, okay. 3 skaters are on a frozen pond. Initially, skater A is at rest, and skaters B and C are holding hands, moving together to the right, as shown in figure 1. So, skater A was at rest, and their holding hands are going to the right. So, skater C then pushes off of skater B. So, this one's moving, but then it pushes off, and then they both continue to the right. But skater C moves away from skater B, as shown in figure 2. Frictional forces are negligible, no friction. So consider the system consisting of the 3 skaters and the system consisting of only skaters B and C. Which of the following correctly indicates which system, if either there is a change in momentum between figure 1 and figure 2? So we know that initially, initially skater A is at rest, then B and C move together, then C pushes off of B, and then B and C move separately. So we know that there's no external horizontal forces, and we want to know in which system does the momentum change. So we have the system of we have system 1 of A, B, and C. And we have system 2 of B and C, right? So, and we know that momentum changes only if an external force acts on a system. So for system 1, hold on, this down a little bit. System 1, we know that the push forces are internal, so no external forces. So that means momentum is conserved. And the forces between B and C, they're internal. And the ice friction is negligible. Skater A not interacting. So again, we have that momentum is still conserved. So we know that the momentum doesn't change in either system. Okay, well, two blocks, one of mass m and one of mass 2m, are initially sliding to the right on a horizontal surface with speed of v and total kinetic energy k initial. There's a negligible force between the blocks and surface. A compressed spring with a negligible mass is held in place between the blocks by a remote-controlled release mechanism, also part of a negligible mass. The mechanism isn't activated, releasing the blocks. The spring expands, pushing the blocks apart. The block of mass m comes to a complete stop, and the block of mass 2m continues to the right. Stop to the right. The total kinetic energy is kf. What's the ratio of kf to k initial? So what we have is, we need to find the initial kinetic energy. So initially we have kinetic energy plus the kinetic energy of mass 1. I'm going to call it, mass 1, and kinetic energy of mass 2. I'm going to call this mass 1, that's mass 2. So then substituting in, we know 1/2 mv squared. And then this one is going to be double the mass, so that's going to be 1/2 2mv squared. So then that's going to be equal to 1/2 mv squared plus mv squared, and that's going to equal to 3/2, same thing as 2/2 mv squared. Now that's k initial. Now we can use the idea of momentum conservation. There are no external forces. So then we know that we have momentum conservation, right? Okay, so then you can write the initial momentum is equal to pi mv plus 2mv, double the mass for the second mass, and that's going to be 3mv for p initial. Now for your final momentum, we know that block it stops, right? And we know that the final speed of 2m, let's just call that equal to let's just make that equal to u for now. So then we can write pf is going to be equal to 2 times mu. So then if you set 3mv equal to 3mu, so we're going to set p initial. Okay. Let the final speed. So p initial equal to pf using conservation of. Okay, let's just highlight this. Then we set those equal to each other. Then we can solve for u. We see that that cancels out. So we have, or no, I wrote that wrong. That's 2mu. So u is just equal to 3/2v, right? And now let's find the final kinetic energy. So kf is going to equal to 1/2 2m times 3/2v squared. So kf is going to equal to m times 9 over 4 v squared, and that's going to be equal to 9 over 4 m v squared kf. So now we want to find the ratio between these two, kf over k initial. That's going to be 9 over 4 mv squared, and our k initial was 3 over 2 mv squared. Those cancel. You can write this as 9 over 4 times 2 over 3 reciprocal when you divide, and that's going to be 18 over 2, and then 4 times 3 is 12. This simplifies to 3 over 2, so the ratio is going to be 3 to 2, and this matches with answer option C. So let's continue on. So a block 1 of mass M1 is released from rest at the top of a ramp of height h initial as shown. The block slides down the ramp onto a flat section and then collides and sticks to a second mass of mass M2, where M2 is equal to M1. After the collision, the blocks have a speed of Vf. Frictional forces between the blocks and the surface are negligible. Block 1 is then replaced with a block of mass 2m1, and the scenario is repeated. Which of the following indicates how the final speed of Vf will compare to the original scenario? Okay, so block 1 m1 and block m2. Okay, we know block 2 is equal to m2 equal to m1. Block 1 was height initial. Okay, this is also frictionless, and then it sticks. Okay. If it sticks, then we know it's perfectly inelastic, right? And then for our new case, we have block 1 mass is replaced by 2m1. We also have the same height h initial, and we also have the same block 2 of mass m1, and it's the same type of collision. So how does this change? So we know up here potential energy, down here we have kinetic energy, and we want to know what the difference is. So the speed, we have to find the speed at the bottom of the ramp. So we can use energy conservation because there's no external forces, right? So then we have the initial energy is equal to the final energy. So that's going to be, so in both cases, it's going to be the same in both cases because height and gravity are unchanged, like we saw in the problem. Like we see that it's the same height. We're still on Earth, so that's gonna be the same. And the reason why we know this it's gonna be the same, like the E initial and EF is gonna be the same in both, is because we use initially we had P is equal to kinetic energy, so it just converts conservation of energy. So we have mgh initial is equal to 1/2 mv squared. Then solving for v, you have times 2 times 2, that cancels out, divided by m, cancels out, that, then you also, that cancels out, the root of this, then you have that v is equal to the root of 2 times g h initial. And what we can see from this formula is that the speed at the bottom is independent of mass. We don't see m in the equation, so it's not accounted for when we're computing this value v. So now we can look at the original collision in case 1. So in the original collision, we know that the momentum before the collision, pi, is equal to m mass 1 times v, and then the total mass after sticking, your m total, is equal to m1 plus m1, so that's going to be equal to 2m1. So that's post stick. Whoa. So then we know that the final speed, vf, of the original, so then we know that's going to be equal to m1v over 2m1, and that's going to equal to v over 2. Now, case 2 for the new collision. And this was when we have, again, we have block of mass 2m1. So then your momentum before the collision is pi is equal to 2m1 times the v. So the total mass post stick, find this too, that's going to be 2m1 plus m1. That's going to equal to 3m1 for m total. Now we find the final speed again. So vf new, that's going to equal to 2m1v over 3m1, and that's going to equal to 2 over 3v. Now we want to compare both of their final speeds. So originally we have vf is going to be equal to 1/2 v versus vf 2 over 3 v. So then we can just take the ratio of this. So we have 2 over 3 v over 1 over 2 v. That's going to be equal to, this cancels out, we have 2 over 3 times 2, that's going to be 4 over 3. So this 4 over 3, let's look at our options. This is greater than 1, so 4 over 3 is greater than 1, and was greater than 1, and it's also less than 2. So then let's look at our answers again. So it will increase by a factor less than 2. So that was long. 2 blocks are held in place on a horizontal surface with a compressed spring between them. The mass of the left block is twice the mass of the right block, and there's negligible friction between the blocks and the surface. Both of the blocks are simultaneously released, and the spring expands, pushing the blocks apart, and then it falls to the surface. The right block has a speed of v, and we want to find the speed of the left block. So I'm going to call this 1, 2. So you can see that there are no external horizontal forces, so we can conclude that the momentum is conserved. And when the momentum is conserved, we can write P initial is equal to 0. So, and then from that we can write that PF is equal to, and we have to define the left block. So let's just call this, U. Let's call that velocity U. So let the left block speed be U moving left. And because we defined that it's moving left in our direction, we don't have to write negative. So, or actually we still want to write negative. So let's do it for a second. Yeah, okay, because we're going to just say, so yes, U will add the negative sign on there. So we have 2m times negative U plus m v. That's going to be equal to 0 mv, because P initial is equal to PF. So these are all one string. So now we have MV minus 2MU. Now solving this, we add 2MU. Then we have 2MU is equal to MV. We can see that cancels, mass is gone. U is going to equal to V over 2. Now, which answer is this? We can just see that it's going to be B. A student drops a brick which falls freely for 2 seconds before landing on the ground. The impulse delivered to the brick by the gravitational force during the first second on the fall is J initial, and the impulse delivered to the brick by the gravitational force during the second is J2. Which of the following correctly compares J1 and J2 and provides a valid justification? Okay, so again, the definition of impulse, J is equal to the integral F dt. And also we know that let's actually write this down here. For gravity near Earth, we also know that F is equal to mg, and that's gonna roughly be constant. And now we can compare the impulses. So 2 seconds falls for 2 seconds before landing on the ground. Okay, so each interval, we can split that 2 second interval into 2, right? So each interval lasts 1 second, and the first impulse will J1, J2. So, and that means we know, and the force is the same. So because we know that, we can write that J initial is equal to mg1. So we know it's J is F, the force times, force times the d. So J2 is equal to mg1. That. And we know that J initial is equal to J2, so we know that force and time are both the same, right? Okay, so force and time are both the same for both intervals, so therefore we know it's going to be C. Now let's continue on with our last 3 questions. So block A of mass 2m moves to the right and speed 2v, and block B of mass m moves to the left with speed v as shown in figure 1. A short time later, block A is moving to the left with speed v, and block B is moving to the right with speed 2v as shown in the figure 2. Was an external force exerted on the two-block system between the instants shown in figure 1 and figure 2? Why or why not? So we know that in figure 1, initially, and figure 2 is the later version. So we can see that we can see that block A is 2m, that's going to be 2v, and then we can see here this is m and this is negative v, because we can define this as positive y and that as positive x. And then and then figure 2, we can see that the velocity here is negative v and then positive 2v. So what we want to know is, was there an external force exerted? So external force, what is external force? External force, it exists only if the total momentum changes. So our question is, did the total momentum change? So we can find the total momentum in both of these systems, right? So the total momentum, okay, let's do this. Total momentum, that's going to be P initial is equal to 2m times 2v remember P is equal to mv, and then you have plus m times negative v. Then you have, okay, so you have 4mv minus mv. That's going to equal to 3mv for P initial. And then later you have in P, actually, let's just, yeah. Okay, yeah, P initial, and then let's just call this PF. And then that's going to be 2m times negative v plus m times 2v. So that's going to be negative 2mv plus 2mv, and that's going to equal to 0. So because we see that, we see these two are not the same, right? So we know that P initial does not equal to P2 because 0 does not equal to, what was this, 3mv. So therefore we know that the momentum of the system changed. So an external force must have acted. So, okay, is it because both blocks reverse direction? No. Yes, because the total momentum in figure 2 is different than the total momentum in figure 1. Yes, that's probably it. Let's read the other ones. No, because the total momentum of the two block system is the same in both figures. No. But no, because the total momentum in figure 2 is 0. Well, yeah, that's true, but like not just that. There's a better reason, which is B. Okay, so let's move on to our final two questions. So a 500-gram cart moves to the right with kinetic energy of 0.14 joules on a horizontal surface. The cart collides with a 250-gram block that is initially at rest. The cart and the block collide elastically, and the block moves to the right with a kinetic energy of 0.12 joules, and the frictional forces are negligible. And we're asked, what is the kinetic energy after the collision? So, okay, we can say the C for cart, and B for block. So cart is going to be MC, that's going to be 500 grams, 2 kilograms. It's going to be 0.50 kilograms. And then the block is MB, that's 0.25 kilograms. So then we have that so we have the cart, initial cart kinetic energy, that's going to be KCI is equal to 0.14 joules, and we know that the block was initially at rest. So that means we know the collision is elastic. So then post collision, then the block kinetic energy, that's going to be KBF is equal to 0.12 joules here. And what do we do? So we can see that, so we know that because it's elastic, right? Elastic means that we have you have total kinetic energy is conserved, conservation of energy. So then you can write that K total I is equal to K total F, right? So then you know that the initial total kinetic energy, Ki, was up here. Ki was 0.14, and no, that's not the total though. So K initial is equal to 0.14 joules, right? And then we know Kf is equal to KCF plus KBF because they collided elastically. They move to the right. So now we can set these two equal because we know we have the conservation of energy, K initial is equal to Kf, right? So then you have 0.14 is equal to KCF plus 0.12. This was from here, 0.12, And then we have this KCI initial 0.14 joules. So, yes. So now after this, we can solve for KCF. Okay, we can solve for KCF. That's going to be equal to minus 0.12 minus 0.12. That is going to be equal to 0.02 joules. So that's your answer. That does not look like joules. So that's going to be answer option B. Which of the following correctly indicates how the internal energy of the black car system changes, if at all, during the collision, and provides a valid justification? So, what do we know? We know that the collision was elastic, right? It was elastic, and we're asked how does the internal energy change? And when we have elastic collision, we know that no mechanical energy is lost, and so that means that no energy conversion to heat, sound, or deformation. So therefore, we know that the change in the internal energy is going to be equal to 0. So let's read the options. Okay, so it does not change because no mechanical energy is lost during the collision. Probably, but let's check the other options. It does not change because the momentum is constant during the collision. It says using energy as your justification, so not momentum. We're not really looking at momentum here. It increases, but momentum is transferred from the car to the block during the collision. Okay, but momentum transfer, it does not equal to internal energy increase. That's not the same thing, so not that either. And it increases because some mechanical energy is transferred from the block to the cart during the collision. So, but like mechanical energy transfer doesn't imply internal energy change. Internal energy change. So, no, and that's how we know A is the right answer. All right, we're done. Okay, for question A, in scenario 1, a block is placed at the bottom of a semicircular track as shown. An identical mass released from rest at height h above the bottom of the track slides down and collides elastically with a block at the bottom of the track. The block at the bottom then slides up and then reaches a maximum height of h max. There is a negligible friction between the block and the track. In scenario 2, the process is repeated except the blocks stick together when they collide. Which of the following correctly indicates the maximum height that the bottom block reaches in scenario 2? So we know that the bottom block reaches a height max. So at the bottom, the block is released from height h, and then it slides frictionlessly. So then we can use energy conservation because there's no net external forces because there's no friction. So we have mgh is going to equal to 1/2 mv squared. So E initial equal to EF. Kinetic energy is, we'll just write it here. Equal to potential energy. And we have, we have 1/2 mv squared is equal to mgh. Multiply both sides by 2/m to cancel that stuff out. We just want v squared, right? So then we have v squared is equal to 2gh. Taking the root of both sides, we have v is equal to the root of gh. So that means that it rises to h max is equal to h. And this is going to be the same in both scenarios because of energy conservation, and also it's the same height. So now we have to examine what happens in scenario 1. So in scenario 1, we know it was an elastic collision, right? And we know that the blocks had the same mass. The moving block stops. In 1D elastic, let's note that in 1D elastic collisions, I want to make some room here. In 1D elastic collisions, we know that the moving block stops and the bottom block leaves with the same speed. Actually, this is kind of messy. Okay, well, that's fine. So that we know then post-collision, the velocity at the bottom is going to equal to the velocity. So then when it climbs up the track, we know the kinetic energy equal to the potential energy. So we know that 1/2 mv squared is equal to mgh max. So then everything cancels out. Then we have h max is equal to h. So then this is what h max actually is. So now, examining scenario 2, we have a perfectly inelastic collision where they stick. The max height is still the velocity is equals to the root of 2gh, and we know that before the collision, the momentum is pi is equal to mv, and then we know that after the collision, it is double the mass. So pf is equal to 2m times vf, and then we can set the pi equal to pf using conservation of momentum during the collision because it was perfectly inelastic. And then we have, solving for vf, we have vf is equal to v over 2, and there's a reduction in the speed because the energy was lost during the collision. So now the kinetic energy, okay, yeah. So then when the kinetic energy goes to potential energy, we know that we have to use the energy after the collision to find out how high the stuck blocks rise, right? So you have 1/2 times 2m times v over 2, and then that squared equals to 2mgh. Yeah, so that's just kinetic energy, potential energy. Yeah, so that you just can cancel out. Yeah, so you can just cancel. So 2 squared, that's 4, right? And then the 1/2 2, that just cancels out. You have over here, you divide both sides by m, and then you get v squared over 4 is equal to 2gh. Then solving for h, you divide both sides by 2g, and then you have h is equal to v squared over 8g. And then now we have, okay, so now we have this height, just in a different color. We have this height, and then we also have, okay, we have from scenario 1, we have that v squared is h max is equal to v squared over 2g. So now we can compare these two. V squared is equal to 2g, yes. So now we have these two to compare to. Okay, let me make this orange. Sorry, it's kind of messy. Then you can take the ratio of, that's here. So comparing this to h max, comparison of the two. So we have that h over h max is going to equal to v squared over 8g, and then we have v squared over 2g. So this is going to equal to 1 over 4 because by. Yeah, and then you reciprocal it because you want to just flip them to the numerator, and then you have 1 over 4 h max. So the height is 1 over 4. So then, yeah, h is going to equal to 1 over 4 h max, right? So this was here, that was there, and that is your h, right? So now we have to find which of these answer options does this match, right? So this is going to be less than 1 over 2 h max because yeah, it's 1 over 4, and we know that that's not right, and then this is not right because, and for C, this would have been true only if no energy was lost in the collision, but we know that in a perfectly inelastic collision there is energy loss. So, and when does that happen? So that loss happens when, it happens like before the block starts. The blocks start climbing. So that's how we know that the height is less than 1/2 h max. So because the blocks stick together, the mechanical energy is lost during the collision. Then that reduces the speed more than in an elastic collision, since the height depends on the speed squared, and the final height is, so that means that the final height will be less than 1/2 of h max. All right.